I know someone is going to tell me that what are you talking about now, but you should have maybe watched a recorded video about this class. So I want to start now if there is no big worry. Is there a query that I could maybe address before? Yes, no? Okay. So binary conversions from decimal actually can even range to numbers which have fraction parts. We have already covered and understood how you could convert maybe such a number to binary. And just to recap a little bit, if you have this number and you wanted to convert to binary, then you have to have maybe some simple table, and you assume that this is your dividend in the middle, and then the divisor is always the binary, I mean is always the base that you want to convert to. For example, in this case, that will be base 2. So I would write the 2 here, and then the last column should always be for the remainder. So if I divide 12 by 2, then I'll have 6 here as my new dividend. And then what is the remainder here? The remainder will be 0. Again, 6 divided by 2, that will be 3. Remainder 0. 2 divided by 3, that will be 1, and remainder 1. So we write the answer in the reverse direction like this, and then you should be having something like this as your answer. That is one method. The other method was just you using weights. Uh, for example, 2 to power 0, 2 to power 1, 2 to power 2, 2 to power 3, 2 to power 4. So if I could stop here, then this will be 1, 2, 4, 8, and this is 16. Then I keep on comparing what number I want to break down to binary is 12. So I look at these weights and I see the weight which is either equal or just less than that number. In this case, I'm converting 12. So 12 is um, not above 8. It's below 16, but it's not even equal to 8. So I could use 8 in this case. So, and I say 12 minus 8. This means that I would have what? 8, and then the remainder will be 4. So if I have 8 and 4, so this could just make for me 12. So these numbers that I used, I'll record the 1 and the 1, and then the weights that I don't use, I just record the 0. So you realize that even this is another method that I showed you. You could maybe review. So that was about the the integer part. Now, assuming I had a fraction part on this number 12, maybe 0 point, can I say 15? How would you tackle this? These are the rules. For the fraction part, which is this, of course, we take the point, including. So I would assume that this fraction part is written as 0.15. And I say that you have to multiply by the base number that you want to move to. and then you keep on recording the carry while the multiplier is always now pushed on the next column. So these are the statements that I'm trying to explain. I'm saying that for the fraction part, it is formed by successfully multiplying the fraction part of the decimal number and recording the carry until the result of multiplication is zero. So whenever you have a zero somewhere, now your new multiplier, you just stop. Actually, you won't record the zero. So the carry sequence is written now in the forward direction. Remember, for the integer part, we are recording things from bottom to end. In the other case, we had 1, 1, 0, 0. So we have to record things like that. But for the fraction part, we shall have to record our carries from the forward direction going down. So if the result of the multiplier does not seem to be ending towards 0, in that case of the fraction part, then the process has to be continued only if the requisite number of equivalent bits has been obtained. So if a number was telling maybe to have bits only equal to maybe 8, okay, 8 bits. So just know that, okay, if I count maybe my bits, are they 8? Maybe something like this. Are they equivalent to 8? Then I have to cancel. I have to stop there. That's when you're not actually heading towards a 0. So in this example I'm trying to give you here, if you had a task of converting 12.15 to base 2, so we said that first step, you multiply it by 2, then you're going to be having a result here, then you record your carry here. The multiply, you're going to again multiply it again by 2. So in this case, 0.15 times 2 seems to be something like 0.3. So in this case, the carry here, the carry is going to be the carry is going to be 3. Is it 3? No. The carry should be this one, the 0, okay, and then the multiply is going to be this 3, okay, something like this. So you have a situation of having a 0 here. But I'm saying that if you, for example, have a 0 at this point in the place of 3, then in that case you have a 0, then you have to just stop. So that might be but that might not have been a good example. So let us look at the example in the PDF, and then we shall have the real concept driven home. So let us use this example here. So we are saying that we want to convert 13.75 base 10 to base what? Base 2. Okay. I won't worry about the integer part because this is something that you already now covered. And if I'm not mistaken, if I use powers here, maybe weights, I have 2, 4 here, 1, then 12 will be, 13 will be something like 1, 1, 1, and then 0. So you have a 13 something like this, but this is now the integer part. What about the fraction part? So you have to convert 0.375. Okay, so first step, 0.375 times 2. We have to have an answer here, and then we carry something up here. So that 0.375 times 2 is going to be 0.75. So in this case, what is our carry? Our carry is this one here, the 0. Then what is our multiplier? The 0.75. So bring the 0.75 here times 2, which is equal to 1.5. Again, the fraction part of this is going to be the multiplier, which you bring here, and then the carry is the 1, which looks which seems to be at now the part of the integer. So that will be a 1 to be carried, and then you have a 0.75 times 2, which is I think should be a 2, I mean a 1. So you have a 1 here, and then of course 1 is equivalent, we know 1 is equivalent to what? 1.0. So it will be the same thing as if you are saying that you are going to now carry a 1 here and then bring a multiplier of 0. So this is now the situation where I told you to stop, because even if now you multiply a 0 times 2, you still be getting what? A 0. So the moment you get this 0 on the side of the multiplier, not the carry, you just stop, and then you record the answer from top to bottom. This time not from bottom to top, but from top to bottom, the forward direction. So be writing now 0, 1, 1. But this is the fraction part. Remember, you have to combine with the integer part. The integer part was this 1,1,0,1.011 base 2. So we could check the answer. Okay, yeah, so the answer is that. You can compare this with this. So the other thing I want to tell you that sometimes binary is written by a prefix of b, but with preceding 0 here. So you write the 0 like this in the computer language. So in this case, you would not maybe see a number like this with a base here as the subscript, but you have something like the 0 and the b. So this just tells you that this is a binary number. Then you 1 1 0 1.0 1 1. So in this case, you won't see the subscript here. You won't see that. So don't get confused if you maybe you reach an exam and then something is set like this, and then they tell you that convert this number to maybe octo. Again, that means that octo could also be written with a prefix like this, 0, then the O maybe with a 5 6 1, and then you are confused, what is this? So this means what? Octo. The other hand could be maybe you're writing maybe hexa. Again, you receive something like this. Okay, so this means that you can have different representations, but you shouldn't get confused. Okay, so that was about converting from decimal to binary, but dealing with now the when you're dealing with the integer, I mean the fraction part. Okay. What about if I want convert from decimal to octal? The process is going to be similar. Only what will change is the radix. The radix, I mean the base number. Okay. So assuming we have a number like this, 73.75. This is base 10. Okay. Convert it to octal. So I told you this one shouldn't be your worry now because I already showed you. For example, if I wanted to convert this to a base 8, then I would just have something like that, or just in form of columns like a simple table. You have your dividend here, you have your divisor here. So the divisor is always the base number, base 8. Then the remainder is what you're going to be storing here. So you have 73 here. So 73 divided by 8, you have a 9 here. And 9 times 8 will give you a remainder of a 1 here. Then 9 divided by 8 will be a 1 and remainder 1. So that means that you have to record your answer like this. This is for the integer part. But now what about the fraction part? Remember, you have the 0.75. The 0.75 is the same thing as 0.75. So step 1, we said you multiply with the base number, the radix, which is the radix you want to move to. This, in this case, it is 8. And you will store the carry. So this is 6, and your carries should be stored here. But 6 is equivalent to what? 6.0. So that means that the carry is going to be what? The carry is going to be 6 here, and then the new multiply is going to be 0. But we said that the moment you see a 0, then just stop there and even don't record it. And then record the carries, the forward, backward direction. So in this case, the answer will be 6 for the fraction part, and yet you had a 1, 1, 1 for the integer part. So combining this, you will have 1, 1, 1.6. But this is base what? Base 8. Like I told you, you could write like this as a subscript, but don't get confused if you have a number written like this. As a computer scientist, I would just know this is base 8. Okay, that is about yeah. So you can compare the answer. The answer is this, which is not different. Then what about decimal to hexadecimal? Just a second. Paul, you should be our timekeeper, please. After 1 hour from the moment the class started, please alert me so that we can do some lab for our practice. Yeah. So 82.25 convert to hexadecimal. Again, hexadecimal. Integer part, for those guys who never attended maybe the earlier classes, this is done, 16, and then the remainder will always go here. So 82 divided by 16, You have a 5 here, and what will be the remainder there? You'll have an 80. Wait. Wait. I have to create some space here. So I'm saying I'm converting 82 to base 16. This is where I'm going to place our remainder. This is the dividend, this is the divisor. So I'm saying that 82 divided by 16, you have 5. So you record the 5 here. And then, of course, 5 times 16 is the 80. So 80, if you subtracted it from the 82, then you will have a remainder as what? As a 2 here. Since you're already seeing that this value is now less than your radix you're moving to, you can now no longer say that you want to divide. Just stop here and then you record this one in the backwards direction or reverse. So you'll have the 52 to be recorded for the integer part, and then remaining to battle with is the fraction part. So you're having 0.25 here. Again, we say that step 1 is multiplying it by the base you want to move to, which is base what? 16. This case, base 16. So what is the answer? 0.25 times 16. You will have a 4. And this case, of course, 4 is the same thing as 4.0. So um, you record um, you record the integer part this side, and then as the carry, choose 4, and then you record the new multiplier as a 0 here. But the moment you see 0, then you have to just stop and even don't record this. Okay, so this answer will be a 4, because you're recording now from forward, backwards to the top, to the bottom. So combining the answer, will have something like 52.4 base 16. But I told you you could now write it using prefix. So you can now write the 0 cross here, and then the x. X stands for hexadecimal. So you'd write something like this. So again, just a reminder, in terms of prefixes, the decimal we don't have. So it means if you have just a number like this, just know that this is decimal. Okay, this is decimal, because unless they are giving it a subscript here, but this is just what? Decimal. For the octo, use the O. So you should know that why I'm writing something like this is to differentiate that this is the number 0, but this is the letter O, standing for octo, base 8. Okay. Then X stands for hex, for hexadecimal, base 16. Then stands for binary, that is um, base 2. Yeah, so please again note that. So if we check and compare with our answer, 52.4, yeah, you can see the answer is here. So we are good to go. If there is a doubt, please you can send a chat or raise your voice for clarity. I'm going now to move to binary octo and octo binary conversions. Of course, we know now that octo is 8, binary is 2. So first example, we want to find the binary equivalent of this number. These are the rules. If you are converting something from octo to binary, because now here our example is telling us to get the binary equivalent for this number. That means that you have to group in terms of bits. So for binary, for base 8, you can realize that if you have to deal with powers 2.0, 2.1, 2.3, where do you have the 8? You get the 8 when you have 2 to the power 3. So that means that we are going to be grouping in threes. Okay? So when we group, there are again some rules that we are going to focus on. Think let us learn by doing. The number we want to learn how to convert to binary is in base 8. This is 374.2. So you see, it has a fraction part and an integer part. So we said that we deal with grouping. So we are going to group in threes, but first of all, convert each individual digit that you see there into binary. Then later you group your threes, both for the fraction part and for the integer part. But like I said, there are again some rules that are going to come into play as you are going to be seeing. This is a 3. So I want to be interacting with someone so that we can have a smooth discussion. Who is ready to interact? By solve your name, and then you can unmute your microphone. First serve, first come. Yes, raise your voice and then interact, please. Yes, what's your name? Okay, yeah, so cool. So first step here, we're going to first convert each of these digits into binary. So tell me 3, what is 3? Mm-hmm. 1, no, it will be 1, 1. Mm-hmm. Then 7, so each one that I'm writing, I'm trying to separate it, okay? So I'm separating, this is for the 3, The next one is 7. What's the binary equivalent? Is it 1, 1, 1? Be sure. 7 is what I'm talking about. Mhm. So this was 3, 3. This was 3, and this is 7. What about 4? Nice. Mhm. And actually, yeah, yeah. So if you want to check your mistakes, always use the weights. Okay. So of course, in terms of weights, you will see that there is a 0, there is a 1 here, there is a 2, there is a 4. So you're only where the 4 is used to get out of 4 which we are converting, you guys just give the 1 there. Okay, so that's okay. Can we proceed? This is the integer part. What about the fraction part? What is 2? good. What about 5? Nice. Okay. Again, if you're not sure, you now give the weights. If I give the weights here, I would say 1, 2, 4. So 4 plus 1 will give me what? 5. Okay, that's nice. That's already now. Okay. 1, 2. So 2 plus 0 because it's already 2. That's also correct. What about the 4? Yeah, we already checked the 4. The 7, 1, 2, 4. This is 4 plus 2, 6 plus 1, that is 7. The 3 is 1 and 2. Yeah, which is already 3. Okay, so you already now have the now have the binary what equivalent to for each of these individual digits. But now we said that you need to group them to their equivalent what? 3 bits. So I'm seeing, for example, on 4, I already have the group of 3. Even that's the case for 7. What about the 3? What should I do to this? I add a 0 on the left hand side since I'm on the integer part. If it was the fraction part, then I would no, it will be still the same thing. Okay, that will be still the same thing. For example, a number like 0, I still have to add a 0 here because this doesn't change the meaning even if you convert back to base 10. Okay, so all these are now grouped as 3 bits. So we are converting to what? We are converting to base 8. Is it? No, we are converting to base 2. Okay, we want its binary equivalent, right? So that means that I'm going to rewrite the whole of this what answer here, and I have something like 0 1 1 1 1 1 0 0. So I'm spacing for your readability. Now, after writing this is not actually your final answer. So we have a rule that for the fraction part, you have to omit any 0 on the extreme what? Right of the whole fraction number. For example, if we had a 0 here, we would omit this 0. We would not write it on our final answer. On the other hand, for the integer part, you also omit a 0, the 0 on the extreme left hand side on the fraction on the integer number. For example, we have to omit this what? This 0. So that means that our final answer is going to be 1 1 1 1 1 1 0 0 point 0 1 0 1 0 1. But because of course I told you that I was spacing these for readability now, I would now write the final answer as 1 1 1 1 1 1 0 0 point 0 1 0 1 0 1 as my final answer. This is in base 2. Told you may not write this and you just write something like 0 cross here and a B. You will still be right. Okay, so you can check if that is right. You can compare where is the number, where is the answer, the binary equivalent. Okay, I think if you compare your answer, this one here, you had 1 1 1 1 1 1 1. There are how many ones here? There are 6 ones, and also here 1 1 1 1 1. There are 6 2 zeros, 0.0101. Um, yes. So do we have a mistake somewhere? Um,
The example is 0.26.
the example is 0.26. Okay. Okay. Yeah. So if we change a little bit about the number, then we should have gotten it right. If this is base what? If this is if this was 5 now, was the this was 6. Yeah. So maybe we could prove if this was a 6. Okay. If this was a 6, what would change? What would change? Let us review our fractional part. What would the 6 be here now? Please, Paul, you're still interacting. What would the 6 become if this was 6? Nice. Then combining it, you would have a 0, of course, after adding this 0 here. So you have a 0 1 0 and then 1 1 0. Okay. But we said that you have to omit the extreme right zeros on the fraction number and then the extreme left zeros on the integer part. So the answer would be 1 1 1 1 1, okay, 0 0.01011 base 2. So does this reflect the same as this answer? Yes. So that's the working. That's when you're moving from octo to binary. What about if you're moving from now binary to octo? Can we reverse the same number first of all? Yes, I think that would be a good approach. So we can first reverse the same number, and we see if we can go back to 3.7 um 3.74.26. Okay, so you're given a number like 1 1 1 1 1 1. Okay, I think there are 6 ones. Okay, 0 0.01011. Base 2, you want to convert to base what? Base 8. So again, you have to group in terms of what? 3 digits, because you're dealing with base 8. Um, so for the fraction part, you group as you're moving from the LSB to MSB. LSB to MSB means you're moving from this side going the other side, because LSB is here and MSB is where? Is here. For the fraction part, you'll be moving from MSB to LSB. MSB is here, LSB is here. Okay, so in this case means you're going to group like this. This one is the first group of 3. This one is the second group of 3. And this one is the last group. So you realize that our last group, we shall need to pad a what? A 0. Okay, Paul, this is still your number, please. Don't drop off. On the fraction part, we said that you move from MSB to LSB. So you move 0, Where should I stop? To 0. Nice. The second time. You pad a 0 here. Okay. After padding this 0, it means that now you have to convert a new binary. This is one group of now 3 bits, another group, another group, um, another group, and then another group here. Okay, so convert now each of these to their respective decimal numbers in that aspect. When you convert these, what do you get? What is 100? It's 4. What is 111? Nice. What is 011? Point. What is 010? What is 110? Then not 6. This is 6. Okay. So this should be your equivalent what? Base 8. Does it make sense? Okay. Yes. Yes, Apo. Thank you. So can I hear from Edwin? Can you interact on this next number? Convert. So you guys, the next one is for you, for your challenge. Try to make sure you know what is happening if you were to convert, because I've just reversed the other one, but you can now try on your own to have this back to 8. Okay, how do you convert? So we have already done that. So we are now moving to another conversion. Adrian, are you able to interact? We're now going to hexa binary and then binary hex.
I'll try.
Okay, so same approach. The only difference is the groupings. In base 8, you were grouping what? Threes, but here we are going to be grouping 4s, because this will be 16, 8, 2. Actually, I'm missing a 4 here. Okay, there's a 1, there's what? The things are weighted like this. So we are going to be grouping 4s this case. That's the only change. All the other rules remain constant. So if we have a number, an example like this, I want you to interact now, Edwin. Help me group it individually to binary.
Okay.
What is 1?
That's 1. We're saying that to the 1 to binary, right? So that's going to be, that's 1 divided by 2. That becomes 1.
It's 1. What about 7?
7 by 2. 3 and 1. 2. That's 1, 1, 1.
Nice. What about the E?
Good. No, I don't remember that one.
Okay, I can help you. This is it. So you remember that I told you that for hexadecimal, if you start from 0, 1, 2 up to 9, the moment you reach 9, you don't write 10, you don't write 11, you don't write 12, don't write 13, don't write 14, don't write 15. These ones are now written as alpha.
Oh, yeah, I
So
remember that.
A, B, C, D, E, F. So remember your conversions. 15 will be 1, 1, 1, 1. Okay. 14 will be 1, 1, 0. What will be the 12?
The 12.
That one.
The 12 is a C, so that becomes. No, I'm confused.
What confuses you? This
So
is
we are
12.
we are converting 12 to. Okay, that becomes 12.
Then 11 will be what?
So 11, that becomes. And that one. 3, 6 day 2, that's 3.
So you remember these weights? You do?
Yeah.
So if I give a 1, a 1, a 1, a 1 here, this is automatically what? 15. So what about 11? Means that I'll have to add this, and this. So 11 will be 1, 0, 1, 1. That will be what? 11, right?
Yes.
And the 10 will just be 1, 0, 1, 0. Like that. Okay, so let's move ahead. What about the F here?
Is 15.
Edwin.
I'm converting.
You have
I need
to.
to write.
The answer is already here. The answer is already here.
Oh, right on top.
1, 1, 1, 1. Okay. So this is something that should be on your fingertips by now. What about the 6?
That's 1. No, it's 0, 1.
1, 1.
1, 1, 0.
0, 0. Am I right? 1, 2. No. Something is wrong here. So the weights always help me to remember. So if it says 6, then I have to give 1, 1, 0. Okay. 1, 1, 0. Yeah. The weights help you to remember this. Okay. So we have now gotten the binary equivalents. But because we want to group them in 4s, we have to give some zeros where necessary so that we have 4 bits. Okay?
Okay.
So the 1 becomes what?
The 1 becomes 0,
0,
1, 1.
0.
No, 4 bits.
Yes.
Okay, it's only 1. Okay, 0, 0, 1. And I was looking at
0,
7.
0, 0, 1.
Yeah.
Okay,
Yeah.
this is the 1. What about the 7 becomes what?
0, 1, 1, 1.
This is just
Sorry,
good
the 4.
to go.
Yeah.
This is just okay. What about the F is just okay. And the 6 becomes
0,
what?
1, 1, 0.
There is another 0 you had.
We said we're putting on the right hand side. On the left hand side.
Of course, that was a mistake. Sorry. Yeah, you're right. So it comes the 1, 1, 0, but the 0 here behind. Okay.
Yes.
So we have now our new binary from hexadecimal as this. Okay. But there is a point here. Oh, there is which group am I missing? I'm missing the group
0, 0, 1.
Okay.
0, 1, 1, 1.
Then
1, 1, 0. 1, 1, 1, 0.
Then
1, 1, 1.
Here.
Okay.
Then
0, 1.
But I said that now this is not the last what step, because we have to follow a certain rule that you have to omit a 0 which is on the extreme right
on the
on the
extreme
fraction
left.
part, and on the extreme left of
Yes.
the zero or the zeros, okay?
Oh, okay.
It's not just one. So in this case,
Comes 1.
yes, I'm going to omit what?
All the zeros.
This one, right?
Yes.
And I also omit what?
That 0.
So I expect my answer to be something like 1, 0,
0, 1, 1, 1.
1, 1, 1, 1,
1, 1, 1,
1,
0.
0, point,
Point.
1,
1,
1,
1,
1,
1,
1,
1.
0,
0, 1,
1,
1.
1. Base 2. Okay?
Yes.
Is it the answer? Uh,
Yes.
is it?
Counting the ones. Yeah.
Where is that number?
It's right on top. You've scored that one.
Okay. This one here.
Yes.
This one here. 1, 0, 1, 1, 1, 6, 0.
Yeah, it's correct.
Okay, yeah. So
Excuse me,
don't
sir.
get, yes, please.
I'm a little bit lost. Can you repeat for me for a moment?
Where are you lost from?
From changing 17E and point F6. Where are you having that red 0 plus the blue ones?
Yes, what confuses you? Converting to binary, or why I added the zeros? What confuses you?
Converting. You first convert fresh. Adding
I need
the
to know.
zeros is
I need
okay.
to know exactly what you don't know by now, because I don't want to teach you again converting 2 to binary, 4 to binary. That is a class that is already
the E.
passed.
Okay. The
But maybe what
E.
confuse you now
You said E is the 12.
No.
Yes.
is
E
13.
is
Is
12.
4.
Is
Is
13.
14.
Is 14 actually.
14.
Is 14.
14.
Mm.
Okay. So when we change it to binary,
So I need to understand your point of weakness. Have you been attending the classes? Are you not
yes,
aware that
yeah.
we have been converting, instead of now writing the 10, we write the A, 11 becomes B, C becomes 12. Is this new to you? This is new to you also?
No, it's not new.
Okay. Then the conversion is the conversion
No, no.
from to binary,
Okay.
the one
Now I
confusing
get it.
you?
Yeah, I have got you now.
Yeah, because I always need to know the point of what
Yeah,
weakness.
I was confused on E, how to.
Oh, yeah, because sometimes it is challenging to take someone
Yeah,
back to
I was confused on E, how it became 1110.
So it's now okay.
On E.
So
Yeah, it's now okay.
So you're going to contribute to the next part of this number, that you get the concept well. So assuming I want to convert this very number back to base 8, I mean base 16, okay? I need you now to interact so that you can get things right. So let's convert this number here. We now convert it back to base 16, okay? So I'm going to first show you, then you do for me the next number, okay? What's your name, please?
Okay.
What's your name, please?
My name is Dennis.
Dennis.
My name is Dennis.
Okay, Dennis. So
Yes.
we are converting this number. We want to see if it can move back to
Yes.
17 E.F6. So since we are
Okay.
dealing with base 16 and base 2, we group in what? In 4 bits, right? So let me just make sure whether
Yes.
everything is written well here.
Mm.
1, 1, 1,
In
1.
4 bits. Yes.
There are 6 ones. Okay. So we group from the LSB towards
Yes.
MSB if we are dealing with the integer part. Then we
Yes.
group from MSB towards LSB if we are dealing with the fraction part.
LSB.
So in this case, my 4 bits here, I have to group like this. I have to take 0, 1, 1, up to 1 here. So these are already 4 bits now. Okay. The next group of 4 stop at what? At this 0. Okay. It means that
At 0.
this one is
Yes.
lacking. The remaining one here is lacking what? Some other 3 bits.
We add 3 zeros.
On the left hand side. Then we move on the fraction part. Start here and then you end
Yes.
here. Okay. This other one,
Yeah.
you start
Yes.
here and then end here, but it is lacking 1 bit.
So
You add
yeah,
a bit
we have to add another 0.
like that. So our new number is now this.
Yes.
Okay. Now we
Yes.
said that
Mm.
after you grouping them, the purpose of you grouping them, you're now going to need
Yeah.
to convert individuals into what? Base 10, because base 10 is
Into
acting as now our intermediate. So which is this one in base 10, and this one, and this one? State the digits.
uh-huh.
Mhm.
This
What
one,
are they?
1, 1, 1, 1.
What is this
It's
one? The first
1,
one.
1, 1.
The 0,
The
0,
first
0,
one,
1 is what?
the 0, 0, 1 is 1.
Is 1. Nice.
Yeah.
And what about the 0, 1, 1, 1, 1?
0, 1, 1, 1. I think it is 1, 2, 3, 4.
Just
It's
recall the weights. 1,
okay.
2, 4, 8. So if you add this, what is what? What is that?
It's 8.
7.
Yeah, 7. Yeah, 7.
And this?
The 1, 1, 1, 0, 1, 2, 4,
That's 13. Okay.
8.
But 13 is written as what? E. Okay.
A moment. 13. 1, 2. Now there, how did it come to 13?
You remember this concept where I told you that hexadecimal, when you reach 10, you don't write 10, you write A. It means 11 will be B, 12 C, 13 D. Actually, this was 14, not 13. Then 14 E. Okay.
Okay.
Then
So
15 F. So
when
that's
we use let's use the weight there also.
the weight will be 1, 2,
Yes.
4, 8. 8 plus
Yes.
4, 12. 12 plus 2, 14.
Okay. Yeah.
Mhm. Then point, what is this one? 15.
Point 15.
Mhm. So you don't write 15, you write what?
F.
F. Nice. And this, then 0110 is what? Give a weight.
011 is a 6.
Nice. So this will be the one in base what? 16.
And base 16.
Yes. When you compare, this is the number.
Okay.
Okay. So Edwin, come back. Dennis is sorted. Edwin, come back, please.
I'm back.
Aha. I want you to finish your bread. So can you convert for us convert us this one here to hexadecimal. The number is 1 0 1 1 0 0 1 1 1 0 0 1 1 0 1 1 1 0 1. Can you convert?
So it's supposed to be grouped in the fours.
Mm-hmm.
So if we group, let's start from where the decimal point is. Can you group
That
for
is
me the four?
LSB. That is LSB. This is MSB.
MSB, okay.
This
And the other side,
this side, this is MSB. This is LSB. Okay. So we group,
fours.
stopping where? Here.
At the one, yes.
Another group.
Then from 0 all the way to 1, the last one, okay.
Another group.
And then I'll need
Then
to
you
add
add
two zeros. Two
add
zeros.
zeros like this. Nice. Then this other one.
0 to 0. 1 to 0. And then add for me 3 zeros.
3 zeros like this. Then what next?
So we will give me
Convert.
the powers. Yeah, we start the conversions.
So if you have the powers here, you have a 1 2 4 8 1 2 4 8 1 2 4 8 1 2 4 8 1 2 4 8 1 2 4 8. What's the equivalent decimals?
So that will be 3 4 plus 3, that's 7 plus 8.
Start from the MSB here. MSB side.
Martin.
The group at the MSB side.
So we are adding those.
So this is 2. The equivalent of this, right?
Only that. Okay.
Huh?
No, I didn't. I think I'm a little bit off. Sorry.
Okay, we grouped the fours, right?
Yeah.
And then we padded the zeros. Okay?
Okay.
Then I gave the weights 1 2 4
It ends. Okay.
8. So what is the decimal equivalent here?
It's
It's
2.
just 2, right?
Yeah.
The first group. Second group, what is the decimal equivalent?
That's
4.
4.
12. Don't
4
you see
plus
the
4
one
plus
here?
8. 4 plus 8.
That
which
is 12.
makes it 12. Yeah.
And 12 in decimal is what? I mean, in hexadecimal is what?
12 is equivalent
10,
to
11
C.
is B, 12 is what?
C.
So you write a C, not 12. And this?
That's going to be
14.
The 12 plus the 2, which is 14.
And you write?
E. That's E.
Point. What is this?
So we move from this side. That's going to be the F.
6.
What?
Where is F coming from?
4 plus 2, which is 6.
Where was the F coming from?
I was adding to make, was it 15? No, it doesn't make sense.
So where is
That's going to
15, yeah?
be
14
8,
still.
4, that's going to be 14.
This is E.
That's the
And
E.
then this is what?
That's 1, which is going to be 8.
This is 8.
It's the 4.
It's 8 because
Yeah.
it's in the weight of the 8 here.
Okay, now I get.
Okay. Where you see the ones, you add the weights. The zeros don't count. That's the idea of this what method. And it is very simple. I showed you 2 methods, and you should by now see the advantages of either way. Okay. If you want to go the long process, use the other long method. But if you master, then this is simpler. So this should be now in base what? 16. But I told you you could find this number written like this. Just know that they are meaning base what? 16. Me, I will be setting my exams like this. I will be telling you convert, for example, convert this to hexadecimal, and I stop there. So if you don't know what that one means, it will be up to you. So let me check. Is that the right answer we got?
Yes.
Okay. Yes, I'm seeing some hands up. What is that? Yes, please. Okay, thank you, our timekeeper. Yes, there is another hand I saw before. Oh, it was you. Oh, I think it was just you. Is there another hand?
Yes, there is a hand.
Okay.
Just can you convert this last question you said? Convert octo 24 to hexadecimal.
What is that one?
This last one you wrote.
Which one?
This octo 24 hexadecimal. The last one.
I was just giving you an example. Now do that one as you practice. You can convert from octo to, okay, let me just give you an idea. Since I'm converting, maybe I have this. Okay, say that I have this, then to hexa. So this is what I would do. Okay, I would just say I need to group these bits because I'm from what? Base 8. So when I group these bits in base 8, I'll have what? 1 0. So who asked this question? Can you please interact?
It's Andrew.
Andrew, So what is 2 in binary? 1 0,
1
right?
0. Yes.
And 4 is what?
4 is 1 1 0 0.
1 0
0 0.
Sure. Okay. So group them in threes.
You add the 0.
So you have this, okay?
Yes, add the 0. Yes.
So what you do after getting the bits in threes, regroup them in bits of 4, in groups of 4. So you have this. If you regroup in fours, what is the answer?
If you regroup in
MSB
fours,
to LSB. I mean LSB
yes,
to MSB.
yes.
What will you have?
You're going to have 0010 as a 4.
This one here,
Then
okay?
yes, then
And this one.
1000.
Then you add what?
0,
Because you
2
want
zeros.
you want now to move to what? To hexa. So convert now this one to decimal. What is the answer here? It's 1.
Yes, that is
And
1.
what is this?
That is, let me see, 1, 2, 4. That is 4.
So this will be your answer.
14. All right. Thank you.
So you feared, eh? You feared just meeting the thing in the exam. Funny.
Okay, thank you.
Okay, so let's switch to practical, because all the concepts here are covered now. And again, let me see my next engagement, and I see how far we have to move. Just a second, eh? Just a second, please, eh? Okay, so when is the next class for you guys? What time is your next class? Hello?
I think we're from different departments.
Yes.
Ours is at, I think that should be at, is it noon? Next class is at noon, 12:30.
Sorry?
12:30.
Okay. I'll stop at 10:15 exactly. Okay, I'll stop at 10:15 exactly. So please time us. Oh, I think there won't have conflict with any class, because I know maybe some other class might be starting at around 10:15. Okay, so we are going to look at some binary representation using switches, and this is just a practical visualization of maybe how your data might be represented, maybe by signals, just a mere looking at the output or the indicators of a circuit. Just assume someone has given you a scenario, and maybe you are in an electronics lab or something like that, and then you're seeing some circuit is giving maybe indicators using maybe bulbs, call them LEDs, maybe they are 4 here or even 8. And maybe sometimes this is off, another time this is off, when this is on, off, off, on. Mhm. And then they tell you maybe that extract for us this data. So the idea is that you already know that off means 1. I mean off means 0. So the binary representation here would be a 0. This is a 1. a 0, a 1, a 0, a 0, a 1, a 1. This is a 4-bit, this is an 8-bit what? Binary representation. Now, if I want maybe to ask this data in terms of binary or hexadecimal, I would know the exact maybe conversion. Even I could now convert this one to base 10. So maybe if I wanted to convert maybe this one to what? Can I say base 10? What would I have? Or hexadecimal. Okay. If it was hexadecimal, then I would have this one as what? 1, 2, 4, 8, 1, 2, 4, 8. Then I would have this is 5.
It is 53.
It is 53. Okay. Yeah. So you as a data scientist, you may need this kind of data, but maybe you are just giving a kind of scenario, just where you have what signals on an electronic circuit. So the lab that we want to do is going to include some knowledge of the semiconductors. I always told you to have some basics about that. So we are going to review maybe some basics of LEDs, switches, resistors, and then I'll create an account on Tinkercad. So as we move on, please search for Tinkercad. You can use this link and then try to be creating an account. Tinkercad. So you need first of all a Gmail account, which I know each of you has, and you'll need to create a personal account. Don't create a student's account or educators, because you need already a classroom that might have been created by me, but not as yet now. So please just create a personal account on that context, and then we move on. So we shall build a simple lab. Our objective is this, that you guys as data science students, you need this knowledge of number system conversions and binary representation fundamental. So this is just going to introduce to you how to observe a 4-bit binary number representing decimal values. Those will be very fundamental in your computing aspects. So materials needed, we are going to use a breadboard, some switches. These are called single pole, single through switch throughs. Yeah, they have four terminals, top and bottom. As you see, we shall need some 4 LEDs, 4 different colors of your switches, and then also resistors and some power supply, and also connecting wires. So you guys who might not have taken time to know about some simple knowledge of the semiconductors, I'll need maybe to just take you through a little bit about LEDs, how they operate, from the concept of a diode itself. Okay, let me try to get this board here. So a diode itself, maybe you guys who might have studied some physics, you could have read through what is called a PN junction, forward biasing. Okay, so P-N junction looks like this. You always have a P side here and an N. So these P types and N types are semiconductor what? Materials that are combined together, and this one in the middle is always going to be called as the depletion layer or depletion region. So you'll always have to have a battery connected somewhere here. So the longer sign here is always the positive sign, and this is the negative sign. So if a battery is connected to a P type side here, the P type side always has positive charges as the majority, while the minority are the negative. And yet the N side always has the majority as the negative electrons, while the positive ions are minority. So in this case, if we give a supply from a battery here, remember current moves in the direction of the positive ions. So these positive ions that are coming from the battery here, they will come and meet the majority of the positive ions in the P type side. And of course, we know like poles always repel, and unlike poles attract. So the positive will be coming and then meeting the more positive ions here. It means that they will have to repel. So we'll see that more forces will push these now positive electrons the other side, okay, forcing this region here, the depletion region, to decrease. So they are forcing it to decrease, because as they come like this, also these negative ions are also moving this side like this and meeting the other negative ions that are majority here. So they also push them, because they are like poles here. So they also push them and close this depletion layer, causing it to almost go away. But now, because the current obeys this direction of the positive ion direction to flow, so current will now, at the end of the day, flow in this kind of what direction. So now, at the end of the day, current will be going in this kind of what loop. So this is what we call the forward biasing, and this is the principle that LEDs follow. That if you supply current in this kind of arrangement, the diode will always allow current flow from the positive terminal, which is called the anode, to the negative side, which is the cathode. So the symbol for a diode is this one, where this is always the anode, which is positive, and this is the cathode, which is negative. But for the LED, we always include these arrows to show that this is now a diode, but it is a light emitting diode. Okay, so that is in simplicity how of course diodes operate. So you can go through maybe this again. I say the link. I remember I earlier again shared it. So you'll see the full working principle about the LEDs. So we're going to use one. You'll see that we shall always be connecting to the positive side, current going through the cathode, which is the negative side. Then we are also going to use a resistor. A resistor has no polarity. So resistors, of course, their signs are like this, okay? Even if you connect a resistor from this end, power will assume that now the other one has become automatically the ground terminal, okay? So current will flow. If this is point A and this is point B, the resistor will still allow flow of current. But even if you change and say that this side I've flipped it and now this side is my terminal B and this is terminal A, and you still follow the same direction, still current will what? Current will be able to flow. So resistor can either be represented like this or like this. The main purpose of a resistor is to limit flow of current. As we shall also later see, we can also use resistors to prevent high impedance in circuits, or what we call floating. In this case, we shall be using resistors as pull up or pull down resistors. So you guys are not going to do like pure electronics, but you just need that kind of what? Simple basics that you can have an idea of how actually your data is really sitting on the real machines. Okay, that's about the resistors. Then what else? The switch. We shall also use the switch. A switch is always having also points like this. So just take an example that a switch is taken to be having like maybe 3 terminals. This is terminal A, B, and C. So this is the input. This is the output where current is going to be flowing through. Then this is like the control that if you close it, then current has to be flowing. So in this case, maybe the switch is connected via a battery here. We have a negative and a positive, and it is going to be helping our LED to light. Okay. So I told you this should be the anode where there is a positive terminal, and the cathode where there is a negative what terminal. At the end of the day, this current will be able to flow through like that. Okay. Yeah, that's about the switch. But the switch model that we are going to be using is an SPST switch, which actually will be having like 4 different terminals. SPST. So you have that. You will see that it has like 4 different to be having 4 different what 4 different switches altogether. So you might see that this is terminal 1A, then this is terminal 1B. Okay. Okay. I think I can represent it like this. Then this will be 2B. Sorry, 2A. 2B, 3A, 3B, okay, 4A, 4B. So we might not be able to use all these. We might just need to connect maybe to only to this one terminal. So from point A and point B. Yeah. So this is going to be called an SPST switch. I'm forgetting the full abbreviation, but it's something like a single pole, single through something. I'm forgetting the full abbreviation, but we shall meet it. Yeah. So then we shall also have to use a power supply. Of course, a power supply could be a battery, as I've been seeing. Of course, there is always a negative terminal and a positive what? Terminal. So on our power supply, we might have just having two terminals where we see maybe one is a red terminal, another is maybe a black terminal. So the black will be always the negative, and the red will be the positive terminal. Okay, so we might need now to connect to get our maybe voltage from this side, and then this will be the ground. Okay, then one last thing that we might need to use, I think, is a breadboard. We just create our long rails to have better connectivity. So breadboard is where you can assemble your different components and prototype your circuit. So it is always having two horizontal rays at the top and at the bottom here. If I'm not mistaken, this is always labeled as positive, this is labeled as negative, positive, negative, down. So if I connected a point, maybe if I already supplied maybe some 5 voltage here, it means that even if I tap from the other end here, still I should be able to get the 5 watt voltages here, because this one is going to be like connected through horizontally. So we'll be seeing some holes. The purpose of these holes is for you to maybe tap in different what connecting wires to get the power from that point. Also, the negative is now where you have the ground, the GND. Still, there is a connection. If I tap from this end, I'll get the 0V, and also from this end, I'll get the 0V. Then what happens on top is what happens on the bottom also. So you can create your rail. Like I said that you have a power supply somewhere. You have a positive terminal and a negative terminal. So you're going to be connecting from the power supply, you supply on this rail. And the negative, again, you supply on this rail. So that next time when you want to tap anything like 5V, you tap anywhere you want there. Then a breadboard is also having some separation here in the middle, some separation. But there is this part above, and there is another part behind here, below. So this one is not horizontal like the positive, negative rails above. No, this one is always vertical. So the holes are organized in a vertical format like this. They are organized in a vertical format like this. Okay, all through long like this. There, even that is what also happens in this other region of B. So it means that if I tap something here, maybe I have supplied, maybe I've connected a wire from 5V here, and I connect it here. It means that there is also 5V here. I've supplied power here. So even if I tap another wire to this point, I'm still tapping on what? On 5V. Because there is continuity vertically here. There is continuity vertically here. And I said that what happens on rail A is what also happens on rail B. Still, you can also maybe supply maybe ground here and say that I'll again tap it from this side. So these are always vertical arrangements, yet the other ones on top and bottom are horizontal arrangement on the breadboard. Okay, so I know most of you have already created accounts now on Tinkercad. Before I switch to now the real thing, is there a question so far about what I'll try to highlight about? I need to get feedback. Are you guys on?
Yes, we are on.
Yes. Is there a question? Is there doubt I could clear?
To me, no doubt, as per now.
And the rest? No. Okay. So let us switch to our thing. We have already gotten the objective of this lab. We have seen that we need to use these different materials, and I've given you a highlight about how we are going to be using the materials. The connecting wires are going to just be hovering from one component, and then you just take that wire to another component of your preference. The LEDs are going to be acting as just indicators of what was switched to them. For example, if LED is on, then the logic of that LED is 1. If LED is off, then the logic of that LED is 0. So the switches are going to be switching on and off these LEDs. Okay. So let me go to the wiring instructions. We are going to be connecting power. We're going to be connecting 8 terminals of each switches to 5V, ground rails to that. So let us move to Tinkercad now. You guys who are already having an account, you can now work with me. Please, I want you to now be telling me that you are not stuck. So I'm going to have I have already my Tinkercad logged in. Already, this is my what? Already, this is my what? Dashboard that I'm seeing. So what you do, guys, if you don't have the account, you need to sign up and then sign in later with that account. And I told you that you log in with, you create a personal account. Don't create a student's account. Create a personal account. So how many? At least I need to get like 5 or 7 people who are already logged in into their accounts, so that I can know that some people are working with me. So, Adrian is logged in. Who else? Ronald, Michael, Resisita. So resistors, of course, still first drag and drop 4 of them, then I show you how to change the values. So resistors have different values. The more the value, the more it will going to be limiting your current flow. So select on any of those and then choose the value type. So I'm not going to choose kilo ohms. I'll use just ohms. So the ohm is this, and then I write here 330. You see when it will change the color codes. Be very fast so that you can spend more time on the analysis. Next, search for power supply. So other people may just maybe select an Arduino board and then to supply for them power to the breadboard, but choose power supply. It's more advanced. So power supply, you will see something like this, which has a 30 V and 2 amps. So on the current, leave it at 5 V. Drop it somewhere. Then what next? Yeah, that's all. Now let's move to the other section of wiring what? Instructions. So we are saying that terminals A of each ST switch is connected to 5V power supply. Okay. And also the ground DND connects to the negative terminal of the power supply. So the power supply is not just going to be connected to each and every switch, yeah? But we are going to create rails on a breadboard. So what you do, come to your breadboard here, and then maybe move this one here, somewhere here, and then say, my positive line, if I hover that terminal, I'll just come and run a a 5V terminal here. So if someone is stuck, please you can inquire. We can help you. Then also the negative. Now take this rail and drive it to the negative what? To the ground of the create a ground rail. Create a ground rail on the breadboard, right? Next instruction is that we need now to create. Okay, now we need to create the connection between each and every terminal of the SPST switch. Connect that one to the 5V power supply. So now our 5V power supply, we're going to be getting it now from the breadboard side, okay? So I could even choose the color of my what? Of my connections here. I could, the connecting wires, I could choose this one color, give this one red and the other one what? Black. Okay. Then I come and I say,
Excuse me, sir.
yes, please.
Mine is not moving like yours. The other
What?
switch, that red wire to the breadboard.
It is not moving from where to where?
it's not moving the way you have moved it to that positive.
Okay, okay, okay. First test with any other component. Hover around the LED and try to you left click, then you let run, then you stop somewhere to make maybe a point of corner, and then again you left click somewhere, then make another point of cornering, like that, and then connect to where you want to go. Does that help? Or you need to display your screen and I see exactly what you're doing.
Yes, I can display.
Okay, please do. Let me stop my screen share and then I try to help you. Mhm. So, um, uh, first of all, press the okay. Hover around any wire that you're seeing. Hover around it until it gets highlighted. Hover in the middle of that wire, and then guess it should be getting highlighted. Then delete it. First, delete all those wires. Then delete. Right. So start slowly by slowly. Click somewhere there and make a point of corner. Click again, make a point of corner. Then take to the positive terminal. Click and then you leave. Like left click, tap, and then you leave that point. There you are like connecting. The mouse should now go minus a wire. If you click and release, hover away the mouse cursor. I see if it's moving.
It is.
No. When you are like moving
escape.
your left click on the mouse and then click and release. You're doing something not right.
Let him press escape.
Okay, even use the escape. So that takes you for practice, my brother.
Actually, if I may say something,
Mhm.
yeah, he was just connecting to the actual sign, not the actual terminal. That's just the sign. Let him continue to that.
Is using a sign? No. I told you
Continue to the
holes.
terminal,
The holes are
the actual hole.
Hey, I actually didn't see that.
Oh wow!
The
Thank you.
holes are the points of connection, not the sign.
I get you.
Okay, so you can stop the screen. This thing was so small, so I couldn't see that. Okay, so next connection is what? We are now connecting each of the 8 terminals to the power. The switches. Okay, so I can say someone should mute your microphone, please. So I don't know how your arrangement might be. Depends on what looks great to you. So all the A terminals, these are the A terminals, okay? But I'm using one side, okay? And then secondly, I said ground connects to the power. I mean ground rail. Okay, this is already on the breadboard. Okay. Then switches connect the B terminals to the resistors. So where are our resistors? Our resistors are here. So move and connect all these guys to the resistors. From the B terminals. Next thing, I need to connect the other side of the resistors to the anode of the LED. So when you look at the LEDs, the leg which is not straight is always the positive terminal. It is always the anode. In the physical representation in the box, you'll always see a representation like this. First look here. In some books and on the physical looking of these LEDs, you will have an LED look like this. Just long like that. But on Tinkercad and maybe other simulation softwares, you will see something like this, just something not straight, and this one. So this means that this is the anode, which is the positive, and also it is the same what? Anode here. So connect accordingly, please. Okay, so I can use this one, and we said that from the resistor you are connecting to the anode of the LED. Then it means that we shall take the cathode of the LED to ground. So that means that I could just bring this one, even if I don't need the wire, I just connect directly to the resistor like that, just to be smarter. So actually, this tells you that you could even remove these wires, okay? Because in the real circuit board representation, sometimes they just solder these things. Directly like that, assuming you are just soldering, this is just fine. Minus even those connecting wires. So I might only need a wire. Okay. I don't want to look so awkward. Like I told you, I don't know how you're going to represent yours, but the smarter the better. You're not smart like me, but make sure you don't confuse yourself. So that is what I have so far. And if I check this, I've connected the cathode of LED to ground, I've connected resistor to I've connected anode of LED to the B terminals of the switches, but through a resistor. So these resistors are acting as current limiting. So it means that if you gave maybe a high value, maybe up to around maybe 100 kilohertz, maybe this one could not light, because the more value of the resistor, then the more it blocks the current from flowing. Okay, so we have finished connecting, and we are now going to do the experimenting or the observations. So we have finished the setting up of the switch according to the guide. Now we want to toggle each of these switches and then make some observations, and then record the binary states of the switches and then the decimal output. So it is now about you to create a simple table and then say that if I switch on only one LED and the rest of the LEDs are off, my binary representation is going to be like this. So this is what I'm saying, that you have for LEDs, LED 1, 2, 3, 4. So it's about you to say that if I switch off this LEDs, this one is on, this one is on, this one is on. What is the respective binary number? To be 1. I mean, to be 0, 1, 1, 1. And what is the decimal representation? What is the decimal equivalent? 1, 2, this is 4. The decimal equivalent will be something like what? This is 7. Then you represent that is 7. Then if I maybe leave them all on, then the decimal equivalent will be what? In base 4. I mean, in the 4 bits, this will be what? 15. Okay. So your task is simply that are you able to quickly analyze that the kind of signal that is indicated by maybe 4 LEDs in a certain arrangement gives you another equivalent decimal value? Yes. So can you be able to answer questions like that? That is what I want to see. But now let us complete this the circuitry testing. So first of all, this is what you're going to do. You see, you have a power supply, but the switch is off, okay? But also you have another button which is called start simulation. So what you do is you can first switch on this. Actually, it won't allow switching. You first have to start the simulation, then you switch, okay? Of course, if you had switched on before, then it is already on now. And of course, because it is just now the power supply, you need now to toggle the switches. So I can now go in my table of observation, and I say the first case scenario is I have all LEDs off. So this is the binary that I have. So my decimal representation is what? Is this 0? And now I go and I switch on one of the LEDs. It is on, okay? I don't know if you guys yours are working. Mine is already working. So I have this as the second what? Observation. Then I say, okay, this is 8. Is it 8? Okay. Then I go and I say, okay, if I switch on the next switch, then the representation will be something like 1100, and this will be what? 1, 2, 4, 8. So this will be 12, which is what? Is it a C? Okay. So this is my aim for this experiment. So the testing is done and everything is working well. So this is your assignment now, that try to make for me a report, and that report should be including a table like this. So show me which switches you're trying to work with. Most preferably, don't use my scenario, because my scenario, as I say, that all of I have these zeros, one only on, it means that the decimal equivalent is 8. When only the third switch is on, then I have this, and the LED display is this. So try to create for me a simple table like this, but avoid the scenarios that I used, and then make sure you can submit these reports to my email address. Since you're not so many, submit my email address for this report. But before submission, I think I should be able to create for you a board on Clan that maybe you can submit there. So don't at the moment send to my email as I earlier communicated. Please wait to submit, but make the report. I'll let you know by I think tomorrow or the other day to allow you maybe submit via Clan. So this should be like your first assignment or lab task, something like that. So I want to close this class if there is no question, but let me give some 2 minutes for any feedback. Yes, Fahad.
Well,
Yes.
I was just trying to ask about the timetable because I thought we were starting the lesson at exactly 10, and I just came in and things are just getting done.
Fahad, you are off track. We have discussed all this from the previous weeks, and we resolved that our classes are always going to be taking place from 8 to 10. I've communicated even this one officially to the academic